for the camera. Can I go ahead? Yeah. Really? Okay. So let me start by thanking the organizers for this very nice opportunity to participate in this early celebration of Eduardo's birthday. And that's an early one, because I'm sure that we're going to have another one in Campinas in October, and this will be a different one. It will be over glasses and glasses of beer. Anyway, but let me briefly say a few words about Eduardo and my interaction with Eduardo. And he came to the University of Campinas in 1985 or 6, if I'm not mistaken, and I had arrived 5 years earlier. And 3 years later, I taught a course on advanced quantum mechanics, and that happened to be exactly on many-body theory. And then, of course, needless to say, Eduardo was one of the best students of that group, actually one of the 2 best students. And there is a very nice story about the other one, who was always competing with Eduardo, and both from the same state in Brazil, and that's Antonio Castro Neto. So once they were discussing, they were arguing about something, and that was a very fierce discussion. And then Antonio came to me and said, "Look at this guy, Amir, he's so aggressive." And I said, "Well, and you are a flower of kindness." and you know, that's a funny story. And then, after that, we discussed a lot those days. Eduardo was planning to leave Brazil and go somewhere in the States for his PhD, and he was trying to make up his mind. And those were the days of heavy fermions and high TC superconductors and all that stuff. And then, you know, we discussed a lot about the possibilities, and I think I lent him a hand, you know, in order to make up his mind. And that's the important thing. And so later on, he went to Rutgers and then postdoc in Florida and so on. And so you all know the story. And then he came back to the University of Campinas in 1996, 97. And then we had the chance to collaborate in our first, the only paper we published together. Because those days I was trying to study the generalization of bosonization using Landau levels for electrons in a magnetic field. And that was the subject of the thesis of Harry Percival. And so when Eduardo joined the department, then we had the chance to interact, and then we published something about the X-ray edge problem in this two-dimensional electronic system subject to a magnetic field. So that was our only collaboration. After that, we discussed physics a lot, of course, and we always discussed the sort of courses we are teaching and very general subjects. And we also share many common opinions, not only in physics, but also regarding music, and particularly politics. That's, I think, we are very closely connected in terms of politics. And but today I'm going to talk about something else. And actually, I was thinking about discussing that, showing that problem of the X-ray edge, but that's late 90s. That will be sort of, you know, quite old. But I'm going to say some words about a very old problem here, that we have developed something recently, but it's about an old problem. So the motivation is old, and that's the following. So what I'm going to discuss today is basically this sort of effective interaction between electrons, effective momentum-momentum interaction between electrons, and I will try to apply that to the diamagnetism of benzene. And that's very old. It's a very old problem. And so that's extracted from the PhD thesis of Thais Trevisan, who is sitting there. And so what I'm going to play with is, I'm going to talk about some generalities and diamagnetism of benzene, as the motivation. Then I'll talk about Hubbard rings, and I apply these sort of models to the diamagnetism of benzene. And then I'll go beyond the Born-Oppenheimer approximation and try to convince you that we can get some sort of momentum-momentum coupling between electrons in these sort of systems. And so there we go. So basically, we all know that, of course, this audience is a very specialized audience, so I can go fast, and I don't need to explain details of things. That usually, we know everything about all the basic interactions about electrons, many electron systems, and but the thing is that is out of reach, really, to solve completely a sort of many-body system, even if we know all the interactions that are relevant for these systems. So usually what you try to do is to use either symmetries or different length, time, energy scales in order to reduce the number of variables and concentrate upon some very specific ones in order to write effective Hamiltonians. And so what we want to do is really to play with effective models. And again, since I'm talking with specialists, you know, we don't need to say much about the nearly free electron model and versus the tight binding model. And if we just add some interaction between electrons, we have the Hubbard model. And other well-known and very useful models are the Fermi liquid model, that you can replace a very strongly interacting system like liquid helium-3 in terms of non-interacting electrons with effective masses and a residual interaction between them. And so this quasi-particle model is very useful. And we can also play with the BCS S-wave superconductivity, electronic pairing mediated by phonons in these sort of quasi-particles in a Fermi liquid, for instance. And then we have this sort of symmetric gap about the Fermi surface. And we can also do that for the P-wave superconductivity. If we talk about superfluidity in liquid helium-3, then we can have either a sort of isotropic phase, which is the B phase of helium-3, or the A phase, which is asymmetric. So an isotropic Fermi gap of these excitations about the Fermi level. And of course, everyone here knows about the Kondo model, and another important effective model is the Kondo lattice, from which we can study the RKKY interactions. And, well, bosonization, we can either use that in a more exact way in one-dimensional electronic systems, or we can also try to generalize bosonization to higher dimensional systems. And so, I don't need to enumerate all these effective models that we know in nature, and people are talking about topological insulators and many other systems. And, you know, a question, is there room for more? Of course there is. The problem is really to try to study the system in a proper way and try to extract, as I said in the beginning, the reasonable and relevant variables for the system. And then, well, that's exactly what I'm going to address here. So the problem of the diamagnetism of benzene is well known since the 30s, and what we have is a sort of perpendicular. You have a plane, the basal plane of the molecule, and then we have an external field perpendicular to that plane, and the susceptibility of the this component, this perpendicular component, is much higher than the parallel component. And that was explained by this very naive classical model of electrons in a sort of hexagonal molecule. And that's the the model that we treat, these pi electrons here, then we have currents, and that will generate some sort of diamagnetism for the benzene molecule, and that's the so-called RCM model, ring current model, and that's the sort of diamagnetic susceptibility that we have for these for the benzene, whether the experimental value is about 10% higher, and so that's the basically the difference between the perpendicular and the parallel components of the susceptibility tensor. And by the way, some comments about things that people were thinking about even in the 30s. London, for instance, was attributing those currents to some sort of supracurrents, and one would think about in recent days, we could ask about the possibility of pairing these sort of systems. Of course, it's a bit strange, but well, actually not so strange, because some time ago, not long ago, there was this paper just claiming that they could observe Cooper pairing from a benzene in a photoemission in this case. So, but I'm not going to digress about this problem here, and so let's jump to the more to the thing that we really want to think about. So that's the let's try to apply. So if this ring current model is useful, and that's a classical model, what about using the tight binding model for describing the benzene susceptibility? And well, so if you have these R's, these are the positions of the ions. Then we have these ions here, just these hybridized s, p, x, p, y orbitals. Then we have these three orbitals, one of them to the hydrogen, the other two for the neighbors. And so what we have is some sort of, that's the picture that we have. And then we can write the Hamiltonian in terms of these overlap, this hopping term between these the side 1 and side 2 and I and I plus 1, and the sort of Hubbard interaction between these electrons. Good. So we have these sigma and pi electrons, and actually what we have here is the following. So every time you have one electron here, one there, and then we can make a sort of linear combination of these orbitals here, and you have these symmetric and anti-symmetrics, bonding and anti-bonding molecular orbitals, and we can put these two electrons there. And so that's the sort of thing that happens here between hydrogen and carbon and so on. But the thing is, the main point is that we have itinerant electrons, the p electrons, and these sigma electrons are the bonding electrons on the chemical bond. Good. So, well, it's quite well known. We can diagonalize this Hamiltonian here for the Hubbard model in terms of these K operators. And then if we have U equals 0, that's the Huckel model. And so that's quite well known. And let me address the following. So what I have here is the Hubbard Hamiltonian for this case. And we studied that for n between this number of ions between 3 and 6, and the electrons always less or equal to n, so below half filling. And so in this case, what we have is these eigenvalues of energy, and we can characterize these eigenstates of energy with this k that will tell us something about the degeneracy of the level. And for the simplest example that we have, we can make n equals 3, so it's a triangle, and with 3 electrons, 1 per side, and that's the sort of spectrum that we have. And if we now go to something, so let me try to explain in a very simple example what happens here. So all these, we have 3 levels, and we will fill these electrons, these levels with electrons, and then we have these degeneracies here, right? So it's easy to count the number of ways we can accommodate electrons in this way here. And so that's the sort of spectrum that we have. And now, let me jump to the important one, to the problem that we have n equals 6 and 6 electrons, 1 per side. Then what we have, I'm plotting here only the lowest lying levels, and so that's the sort of a picture that we have. And then, instead of 3, what we have is something like 6. We have 6 levels here, 1, 2, 3, 4, 5, 6, like the same sort of design as for the benzene. And so these are all, that's the spectrum of energy that we have. And now, let me concentrate a bit on these degeneracies. And what we can do, if you write the electric current for all these levels, we can say the following. There are some states, we just take one of these eigenstates, it should be n here, and then we add all these guys within one degenerate subspace. What happens is that there are subspaces where I can find one specific linear combination where there is a sort of a finite current in the ring. And for some other cases, what we can show is that there is no way to accommodate a finite current in these subspaces. And what about the presence of the external field? If I just write the external field in terms of this fraction of the total flux divided by the quantum of flux, we can write the Hamiltonian in this way here. So what we have to do is to add this phase factor, depending on this ratio, to the kinetic energy term. So, and if we do that, we can find, for instance, the current for all these levels. And again, for 6 ions and 6 electrons. So that's exactly the prototype of benzene. So that's the levels that we have for U divided by T, 0, 3, and 6. So we have the ground state for the system and for 3 different values of U. And so that's the current that we have here. So as we start to increase the current, we jump from this sort of description of the blue line to the red and to the yellow line. So that's the current that we have for these Hubble rings. And so we can try to apply that, use appropriate parameters to describe the susceptibility of benzene, for instance. And that's exactly what we can find, you know, that that's the value of the susceptibility. And using the hopping 2.5, the spacing like 1.4 angstroms, we can find that our molar magnetic susceptibility will be given by this value there. 1.9, but 1.9, you see, is less than RCM, which is minus 4.9, and the experimental value is 5.4. And the thing here is that then we can say that, okay, fine, the RCM is certainly too naive, but the Hubble model is not suitable for this problem, right? And that's, it was even worse than the ring current model. And the question now is, what about other effects like phonons, next nearest neighbor interaction like Hubbard V, and so all these things we can try to improve the model. And so what we propose here is to improve the model by asking about the bonding electrons. What is the role played by the bonding electrons if I try to describe the motion of itinerant electrons? And let me try to explain the next 5 or 3 slides. They will be a bit, you know, heavy, but let me try to explain you in a nutshell what exactly I'm talking about. What I'm going to do is the following. I'm going to consider these bonding electrons and the itinerant ones. The itinerant electrons, they are very slow, right? You can say, but the bonding electrons, they are fixed. Yeah, they are fixed, but the point is that this low motion of these itinerant electrons is due to the hopping T. On the other hand, what we have is some sort of excited states for the bonds. And the excited states for the bonds, it has energy, an energy splitting, which is much higher than the bandwidth for the itinerant electrons. So what I'm trying to do here is the following. I will concentrate upon the itinerant electrons as its low configuration, right? And let's take pictures of this low configuration, and then let's study what happens to the bonding electrons, right? That's exactly the same that we do in vibrational levels in a molecule. So that vibrational motion is very slow, and the electronic motion is fast. So I will regard the bonding electrons as the fast ones, and the pi electrons as the slow ones, right? So that's the idea. And what I'm going to do is that, oh, then you can say, fine, but what you're going to find is that since these electrons, the bonding electrons, are frozen, what happens is that I will reproduce the former model, and no gain, you know, in terms of no new physics about it. So, but then we can ask, is that all there is? Born-Oppenheimer approximation? No. What you can find is some sort of correction to the Born-Oppenheimer approximation. And that's exactly what these next 3 slides are going to show you. So that's all standard textbook Born-Oppenheimer approximation regarding pi electrons as low ones and bonding electrons, sigma electrons, as the fast ones. So, so that's exactly the idea behind the whole thing. And now, okay, fine. What we have here is the following. So that's the Hamiltonian for the pi electrons, right? And the Hamiltonian for the sigma electrons regarding R, the position of these pi electrons as a parameter, right? And so we have 6 pi electrons, 12 sigma electrons, and then we perform exactly the Born-Oppenheimer approximation I was telling you about. These R are the position of these pi electrons, and small r, the position of sigma electrons. So if we do that, okay, so the Born-Oppenheimer ansatz, as I told you, standard textbook Born-Oppenheimer approximation regarding big R as these low variables and small r, the fast ones. And so if we do that, we end up with, I will not bother you with all these steps. And so for the pi electrons, that's what we have now. And this guy here, for instance, will be, for these pi electrons, these R, for the, these HB, the big R is a parameter, right? So doing all these things here, we can write the sort of Born-Oppenheimer, the general expression for these pi electrons in terms of this correction here. And this correction here, it has to do with these Laplacian operators of all these small variables acting on these fast variables. Okay, so that's what we have, and this lambda there will be the difference of energy or different configurations for phi nu, right? So in this case, that's exactly what we have. Lambda naught, lambda 1, lambda 2. That's playing the role of the vibronic potential for this ionic motion when we have molecules. In our case, ions are completely fixed. I'm talking about slow and fast electrons. That's all I'm talking about. So then in this case here, we have this slow motion for the pi electrons, and that's the configuration, the energy of the configuration provided by these fast bonding electrons. Good, so let's jump to another one. And so what we have here is this, suppose that we talk about lambda 0 and lambda 1, only at 2 levels, and then these are the couple equations for the pi configuration and the ground state and the excited one. So in this sense, what happens is that this A that has to do with the matrix elements of those sigma electrons, they are acting and they are coupling these two bands. And so what we can write, if we decouple these subspaces, what we have is the Born-Oppenheimer approximation for 1, Born-Oppenheimer approximation for 2. Fair enough. The thing is that we want to couple them. And if we couple them, let's just rename these guys here. Small n is just the pi levels when they are not excited, and this big N when they are excited. So what I'm going to do is basically naive Wigner-Brillouin perturbation theory, right? Again, textbook. And so if we do that, let me go a bit faster. And so what we can show is that that's the sort of Wigner-Brillouin expression that we have for this coupling between this lowest band and the first excited band of these pi electrons. So again, and this any mu, these are basically these p square and p matrix element between these two sigma electron states. Okay, when you do that, if you believe me, okay, let me try to make a long story very, very short. We can jump from all these approximations and end up with something like this, which is the, okay. So what we have here is one effective interaction between electrons, between pi electrons, right? Which is something like this n are just the unitary vectors pointing towards the center of the ring, for instance. And so we have momentum, and this sort of operator here, I will use something like a local approximation, like we do in the Hubbard model for U, right? I'm just trying, I will consider that only local. I will say that this is a local contribution, and then we have this sort of Pi-Pj interaction. So if we just write that in terms of the second quantized form for localized orbitals, we end up with something like that. So we have one term that is u divided by t square, this coupling, which is t to the fourth divided by lambda cube. This big lambda here, big lambda is the splitting between these two molecular orbitals, right? So that's the effective interaction that we have. And okay, let's try to make it even easier in order to describe exactly what we have here. I will replace that by a general, these guys are order 1, so I will replace that by a T4 divided by omega lambda cube only. And so that's the Hamiltonian that we have in the end of the day. It is the Hubbard Hamiltonian and this interaction term. The interaction term is exactly the one that I just presented you. It's this one here. And this lambda is T4 and big lambda cube, right? So that's the sort of parameter that is useful in order to establish this Born-Oppenheimer approximation. And but then we are playing with two things here. One of them is to say that our pi electrons are slow. So and that means that this guy here, T cubed divided by lambda cube, is less than 1, right? And the other one has to do with the Wigner-Brillouin perturbation theory. So in the end, what we have is a couple of processes. One of them is a sort of bubble, and the other one is a delocalized one. That what we have is we tend to destroy one electron 3 sites, and we destroy one here in the middle, take this one here, put it there, and put the other one on the other side. So it's a sort of pull. It's pulling. One electron is pulling the other one, especially because we have this minus sign there, so it's attractive. Okay. So let's, and that's the picture that we have for one of the models that we were playing with, namely the n equal 3. But now we can go to the important one. And these are the lowest line levels. And when we use this sort of approximation, we change drastically this guy here. So we have this guy bending downwards. So it will become more and more negative because of this term there. But the question is, how far can I go with this u divided by t? And we cannot go just for any sort of arbitrary value. And so in this case, these are the energies for u over t 0, 5, and 10. So that's the ground state with no u. And then we start to turn on the Hubbard u. So that's what we have. And the currents are given by that in terms of these same u divided by t. So that's in terms of the ratio of the total flux divided by the quantum of flux. Okay, so now the thing is, if we use reasonable parameters for the benzene, like 2.5 eV for T, U divided by T like 1.2 and A 1.4, and the conditions for the validity of this extended model is T divided by lambda must be less than 1, and U divided by T must be less than T by lambda 3/2. And so we have very strict conditions there. We cannot go to very, very high U divided by T. And so we are, in a sense, working in a moderate U divided by T regime. Right? So in order to cope with these two conditions of the adiabatic approximation and the perturbation theory, what we need is really a moderate Hubbard U. And so these are the main results there. So we have these delta chi for different values of lambda divided by t. And though you can pick one of them and see what happens if we plot for this fixed u divided by t, if I plot this, if I change lambda divided by the hopping term. And this is the experimental value, right? And so we see that close to 1.1, or actually 0.11, we see that we have some sort of agreement between the experimental value and our results. And for this sort of value, for instance, big lambda divided by t, order of 2.1, that means that we will have lambda order of 5 point something electron volts, which is quite reasonable for the splitting between these bonding excited state for the benzene. And the last picture here is only to show you the contribution of the two processes, the one which is a localized one, like the bubble, and the one which is the extended one. So we have, in a sense, good agreement with these numbers, if we take into account this sort of interaction mediated by virtual excitations of bonding electrons, right? So that's the bubble and the localized processes. And coming to the end, what to say is that, well, although it's not a very good model to play with the aromatic molecules, we can try to add some effective interaction between pi electrons mediated by the sigma electrons. And this new term makes the ground state energy of the molecule more negative, provides, maybe even you can think about pairing, but I'm not saying, I'm not saying defending any sort of pairing in this system, right? So, but you know, for those who believe it, maybe that will be a way to face pairing in these systems. Provide us with more intense, persistent currents in the ground state of the rings, in the presence of the fields, amplifies the diamagnetic response for the systems, and of course, the low competitions between diamagnetic and paramagnetic responses. That depends on the sort of filling that I put in these finite systems. Then we'll have competition between diamagnetism and paramagnetism within the molecule, depending on the sort of excitation of the system. And so, well, we can always ask, but come on, what you're saying is that you incorporating some bonding electrons there, and what about performing a general calculation, so with density function or whatever, in order to incorporate other electrons in the problem? Yes, we can do that, but maybe we have just sort of accidentally select the most relevant of these interelectronic interaction for our specific purpose. Right. So that's one possibility, and that's not the first time that one can see a momentum-momentum coupling in electronic systems. If we go back to the seminal paper by Bohm and Pines of the electron gas, 1953, so 70 years ago, so we can have two contributions due to the electromagnetic coupling between electrons. The transverse one, which is bright Darwin, maybe we can, this order of V divided by C square, and they forget it. And the other one is some sort of longitudinal effect mediated by the electromagnetic field, which is due to plasmons, basically. And in this case, we can also say, well, if we have screening, we can also get rid of this extra term. And that's exactly what we did, what he did in this paper here. They did in this paper. They neglected that completely. But we're not talking about a very strongly screened system. So maybe that's one of the reasons why we can keep this term and find some sort of reasonable result out of this. And so maybe we can also ask about the applications of this sort of extended Hubbard-Hamiltonian to other systems like carbon systems like graphene, pyrolytic carbon, and cyclo-18 carbon. Maybe there could be a sort of a correction or some sort of a new effect if we take into account this sort of interaction. And finally, what about the application of this sort of idea to other low-dimensional, strongly correlated systems? Well, these are only questions, and inspired by this success that we had, just to fit these parameters and see that they can really give you an answer for this very high diamagnetic susceptibility of benzene, for instance. So I think that's all I have to say. I like to thank you very much. And that's all.
Thanks for a very exciting and interesting talk. But I've noticed actually a theme that seems to be common with some other talks. In particular, Oscar Wafek presented, I think yesterday, a talk where he said, well, in Moiré systems you have a narrow band with low energy electrons, but there are these other bands which are similar to your sigma electrons. And then what they try to do, and not only him but many others, is to integrate all these other virtual processes to all these other bands and derive the projected interactions on the low energy sector. And the claim is that this can actually be done through some randomization group method, even in the strong coupling limit. So I was wondering, I don't know if you've heard his talk or whether, maybe Oscar has comments, whether these methods can be used here to go beyond small u, maybe.
Well, no, I can't. Okay. So you just say that there could be a sort of contribution to that too, or
Well, I mean, I've noticed that at least at face value, I'm not working with either one, but it seems a similar problem. And I'm wondering if, you know, I just posed the question.
Oh, I don't know. I don't know exactly what the problem he addressed. He or she, I don't know. Maybe we can talk later. It's,
actually, this is a very interesting talk. I thought I understand chemistry, but after listening to your talk, I realized I still have a lot to learn. So, but a quick question is, I understand that you're trying to use this quote-unquote higher energy electron, which is the bonding, the sigma bond, to somehow screen and dress the slower pi bond, right? And then generate additional contribution.
Yeah.
But from a naive point of view, wouldn't you also think about the fact that this bonding electron, even though they have a big gap when you have a bonding anti-bonding gap, but this gap actually comes from kinetic energy.
from what? Sorry?
Kinetic energy. It comes from the hopping between them, right?
Sure, yeah.
So therefore, wouldn't you expect that if you add a magnetic field and you can attach a flux to those hopping,
okay, fine.
the bonding state themselves could in principle be in the rotating state as well, right?
I can only answer your question if I really, of course, we said, fine, we have these bonding electrons, and of course, this will not be affected by the magnetic field.
That's my
because
question, why not?
They are quite localized. In order to see any sort of transition or any sort of deformation of these electronic clouds, the bonding ones, due to the external field, I don't think it's, I think it will be much, much smaller than any sort of thing that I'm taking into account here.
But this is my question, because a priori there is an energy protection, which is the bonding anti-bonding splitting, which is very large, right? But that protection is not a potential. It is kinetic energy themselves. So if now you add a magnetic flux, the hopping start to, if you do a minimum coupling, you will attach some phase winding to the hopping. Then naively, one would think that the bonding state themselves would have a current already flowing.
But again,
that would be
in order to have
right?
this, well, as far as I understand your question, in order to find the sort of deformation that you're talking about, I need to go into the sort of structure of this hopping term. Namely, we have these overlaps of the wave function, and that will be very small. Okay.
But this is the Lorentz force,
so
right? This is the Lorentz force.
But this term.
A fully filled band does not mean that they cannot have host the current. I'm not so sure.
Discuss that later. Rafael?
Amir, no, just I wanted to follow up on, I mean, it's a comment to a comment, so, but to what Vlad was saying, I mean, Oscar is here, but I was just going to say that when he did this procedure in twisted bilayer graphene, so you also have a hexagon formed by the Moiré superlattice, and when he projects the interactions, he does get a term like yours, which you call the localized, I think they call this assisted hopping interaction.
I see.
So I agree. So
okay. So
there may
I
be
remember that we.
I don't know, but I agree with what Vlad was saying.
With the okay, fine. This question, I knew it was going to show up here, and that the assisted hopping. Okay, that's the term we're talking about. Yeah. We compare that to the term when you get that sort of term, you get something that is not, you're not really getting that term from momentum-momentum coupling. You're getting something, I don't know where from, but some sort of projection, whatever. And as far as I can remember, please tell me if I'm wrong, but when we compare that to assisted hopping, that is well known in the literature, we found that our term is different. Okay? So, and especially has an opposite sign, if I'm not mistaken. So it's different. And this one, I can really work in first quantized form up to a very final point. And then I have pi, pj. And then I can say, okay, fine, let me write the expansion in terms of second quantized or localized orbitals or whatever. And then we get this sort of assisted hopping. But it's not really assisted hopping. It's a bit different. So these are really mediated by, these are momentum-momentum. It's more like a BO-SAIFR sort of coupling. And, but non-relativistic in a sense. Because if we take only transverse contributions for the electron, if we say, okay, this guy here is a charged particle, this other one charged, and then they will interact by current coupling. That in turn, then you have two terms, as I mentioned, for the Bowman-Pines old paper, that the transverse part is relativistic, forget it. The second one involves this longitudinal deformation of the charge. And then we find something like that. To my mind, that's exactly the origin of our term. Then we got that doing something else, maybe a correction to the Born-Oppenheimer, and that was it.
Got one more question, Thomas?
Yeah, I just have a very short question. So the old ring current model seems to gotten a value very, very close to the experimental value, right?
Yeah, well, it's
based on what
10%.
Yeah, exactly, right. Based on what you told us after that, that looks like an accident that they got so close. Would you agree with this?
Sorry?
Based on what you told us after this,
yeah.
To me it looks as if it is an accident that the old model got so close.
Oh, okay. Well, I said accident, but for another reason. In a sense, that's fine. Okay. If we use, a very powerful numerical technique or simulation technique in order to reincorporate all these electrons that are hidden there in the system, fine. It's something that you can operate, and then at the end of the day, you say, okay, I have a good result. But fine. You look at that, and you don't really understand what is going on. What's the real physics you can extract from this thing? And doing that, we say, okay, fine, maybe this sort of current coupling is one of the channels that is responsible directly for this 10% in the, not only 10%, regarding the Hubbard model is much more than that, because the Hubbard model was really, a very bad result. So,
thanks a lot. Before we close the session, remind you that at 2 we resume with the colloquium by Gabriel Apley. So let's thank Amir and all the speakers of the session.